Hello, everybody. Hey, this is our review for the gravitational quiz practice. And our first question was calculate the force between two 60-kilogram objects. All right, so remember that our force of gravity is equal to big G m1 m2 over r squared. And that would be big G 60 squared divided by 4 squared. And you can certainly do that and add the G in there, but there's a lot of times where if you just leave the G at the end, it can be a little bit less confusing. But anyways, we're going to have 60 squared divided by 4 squared, which is equal to 225 times G. So now we're going to multiply that by 6.67 times 10 to the negative 11th. And we're going to get 1.5 times 10 to the negative 8th. Okay, so 1.5 times 10 to the negative 8 newtons. Okay, so that is the force between two 60-kilogram objects that are 4 meters apart. What's the gravitational force? What if this was tripled? What if that was tripled? Now, we can obviously put in 12 squared, but remember that it is inversely proportional to the square of the distance or the radius. So what's going to happen with that, that's just going to go down by a factor of 9. Okay, so we can take that answer divided by 9, and we're going to get 1.67. So this was question number 1. Question number 2 is going to be 1.67 times 10 to the negative 9th. To the negative 9th. Okay, because we're going to take this number divided by 3 squared, which is 9, and that's going to give us this because of the inverse square law. All right, now what happens? What is the gravitational force at the center of the Earth? In case this is not obvious, it is 0. Okay, so remember that a force is a vector. So if you're sitting here at the middle, you're going to have all of these bits of matter, okay, and they're going to be pulling on you, right? So you can just think of a cylinder as a gazillion pieces that are the same distance, and because they are all attracting you and you attracting them, all those vectors are going to cancel each other out, okay? So all of the Earth there. So the answer to number 3 would be 0. Okay, so in our next question or series of questions, we're going to have a diagram that looks like this. Okay, so we're going to have 3 masses that are going to be arranged, 3 masses that are going to be arranged as such, and the distance between them is 0.2 meters. Okay, and question number 4 says, determine the force of gravity, magnitude, and direction on mass A. So what's going to happen is there's going to be the force from B that's going to pull it this way, and the force from C that's going to pull it this way. And because they're 2 vectors, we're going to get something like that. Now, this is something where we know that our force of gravity is equal to G m1 m2 over r squared. Okay. Now again, this is really much more convenient to save the G to the end. Okay. So what we're going to have here is we're going to have 1 times 2 divided by 0.2 squared. Okay. So 2 divided by 0.2 squared is going to be 50. Okay, so we're going to have this one is going to be 50G. Okay, And then we're going to say 1 times 3 divided by 0.2 squared. So 3 divided by 0.2 squared. And that's going to give us 75. Okay. So now we're going to have this vector right here. That's going to be 75g. And now if we want to know, you guys, if we want to know what that hypotenuse is, it's just going to be Pythagorean theorem. So we're going to say 75 squared plus 50 squared is 8125, and we're going to take the square root of that, and we're going to get 90. Okay, so this vector right here is 90 times g. Okay, and again, we will expand that out momentarily. Okay, but the first we want to get is that angle, and we're going to say inverse tangent of the opposite, which would be 50 divided by the adjacent, which would be 75. So inverse tangent of 50 divided by 75 is going to be 33.7 degrees. Call it 34 degrees. So we're going to take 90g, okay? So 90 times 6.67 times 10 to the negative 11th, okay? Which is going to be, and this is number 4. So 90g is equal to 6 times 10 to the negative 9th newtons, okay? And that's going to be at 34 degrees above x axis, okay? So you can see that if you leave that g off until the end, it makes things a lot nicer, okay? And we're going to end up with the same situation here in question number 5. Determine the total energy. Determine the total energy of those series of objects there. Now, this is sometimes called the binding energy because they all have potential energy relative to one another, right? Because these two are acting as a force on this one, but this one and this one are forcing this one. So anyways, we have a potential energy, okay? And that potential energy is equal to negative g m m1 m2 over r, okay? So if we want to do all 3 of them, because we're going to have to do 1, 2, 1, 3, and 2, 3, we can factor out this negative g. So we're going to have negative g, and this is going to be m1, m2 over r12, okay? So this is going to be 1 times 2 divided by 0.2 squared, plus the next one, which would be 1, 3, which would be 1 times 3 divided by 0.2 squared, okay, plus this one and this one, which is going to be 2 times 3 divided by, now the distance, you guys, the distance between those is going to be 2 radical, or 0.2 radical 2, right? 0.2 radical 2. And by the way, these are not squared. Not squared. I kind of got that messed up. Okay, so we're going to have 2 divided by 0.2. So that's going to be 10 plus 3 divided by 0.2, which is going to be 15, which gives us 25. And now we're going to say plus 6 divided by the quantity of 2 times the square root of 2. And that is going to be 27.12. And I just want to double check that 6 divided by 2 radical, that would be 2.28. Yep, okay. So, one second, guys. Something in my brain is a little bit off. Okay, so 27. Okay, so this whole part right here is equal to 27. Now we're going to multiply that by negative g, 6.67 times 10 to the negative 11th. Times 6.67 times 10 to the negative 11th, negative, and we got 1.8 times 10 to the negative 9th. 1.8 times 10 to the negative 9th joules is that potential energy. Okay, and that is the answer to, let's see, that is the answer to question number 5. Okay, so this is number 5. All right, so moving on to question number 6. Calculate the acceleration due to gravity on the moon, which has a mass of 7.36 times 10 to the 22nd and a radius of 1.74 times 10 to the 6th meters. All right, so you guys remember that the force of gravity obviously is equal to big G. In this case would be the mass of the moon times whatever mass we're talking about divided by the radius of the moon squared. And that's the force of gravity. But remember that force of gravity is mg. Okay, so those two m's are going to cancel out. So whenever you want to calculate just the acceleration due to gravity, it's going to be big G times the mass of whatever planet, asteroid, moon you're talking about, divided by its radius squared. Okay, so we can now say 6.67 times 10 to the negative 11th. And our mass again was 7.36. 7.36 times 10 to the 22nd. And our radius is 1.74 times 10 to the 6th. And that does get squared. Okay. So 6.67 times 10 to the negative 11th times 7.36 times 10 to the 22nd divided by 1.74 times 10 to the 6th squared. And we are at 1.62. Okay, so our gravity on the moon, or acceleration due to gravity on the moon, is 1.62 meters per second squared. Okay, and that is about 1/6 of it on the Earth. So if we multiply that by 6, we're at 9.73. So about 1/6. All right. So our next question. If the mass of the moon was doubled while the radius stayed the same, what would happen to the acceleration? Okay, so all we have to do here is look at our equation. So if the mass gets doubled, it's in the numerator, and therefore the acceleration would go to number 7. The acceleration would go to 3.24 meters per second squared. It would just double. Okay, and number 8, if the radius were doubled and this mass stays the same, what would happen due to gravity? And now we're going to take 2 squared, which would be 1/4. Okay, so we would take 1.62 divided by 4, or 2 squared, and we get 0.4. So number 8, it would be 0.41 meters per second squared would equal to G in those cases. All right, so those are pretty easy. They have to do with the, again, with the inverse square law. And now we are going to move on to question number 9. And question number 9 is asking us, at what altitude above the Earth's surface would the acceleration due to gravity be 4.9 meters per second? Okay, so now we're going to have this equation. G is equal to big G mass, this time of the Earth, divided by the radius squared. Except this time we're looking for what our radius is. So radius is going to equal to the square root of big G mass of the Earth divided by RG, which we want is 4.9. All right, so we're going to have 6.67 times 10 to the negative 11th, 5.98 times 10 to the 24th, divided by 4.9. And then we're going to take the square root of that. And we are going to get 9.0 times 10 to the 6th. Okay, 9 times 10 to the 6th meters. Okay, you guys, this is not our answer. Okay. That is certainly, you guys, that is certainly our calculation and what our R is, but we want the altitude. So we're going to subtract away the radius of the Earth, and then we're going to get the altitude. So we're going to take this minus 6.37 times 10 to the 6th, minus 6.37 times 10 to the 6th, which is going to be 2.95 times 10 to the 6th, which would be just a little bit less than 3,000, meters. Okay, now you guys, this is certainly easy to do, but notice here that the 4.9, our 4.9 here was half, you guys, was half of our 9.8, right? So essentially it's going to go up by the square root of 2, So if we take 6.37 and then we multiply that times the square root of 2, we're going to get our 9 times 10 to the 6th, and then we can subtract our 6.37, and we're going to get our answer there. So I just want to double check this. 9 minus 6.37. This is 2.63, not 2.95. I'm not sure where that number came from. Obviously, just plugging it in sort of incorrectly. All right. So you guys, our next questions are going to kind of talk about the Kepler's laws. So what number are we on? That was number 9. Okay, number 10. Actually, number 10 is really easy. The force of gravity is far weaker than the electrostatic force. Why then does the force of gravity dominate the macroscopic world? And we talked about this early on in the lecture about gravity, is because gravity only attracts, whereas electrostatics, okay, opposites attract, but similar charges repel. So much of the electrostatic forces, even though they're a bazillion times greater, they cancel each other out. So we don't really feel the dominance of the electrostatic force. But that if we think about just touching something and just putting a little tiny force there, that is really the electrostatic force of repulsion is really responsible for us kind of being the electrons being really close with technically not touching. All right, so that's number 10. All right, so I'm going to stop here and we're going to erase some things and we're going to go on to 11 through the rest. All right, ladies and gentlemen, we are back with number 11. Okay, what is the shape of all orbitals? Now, according to Kepler, they are ellipses. Okay, and that is our answer. So they're going to be like that. And you've certainly heard me say a lot of that the moon orbits the Earth in a circular orbit. The Earth orbits the sun in a circular orbit. Remember that all circles are ellipses, but not all ellipses are circles. So it has to do with the eccentricity. And if you guys remember in that lecture, that is the ratio of the C over A, center of our major axis. And when you get that ratio, 0 would be a perfect circle, and a 1 would give you essentially a straight line. So if you have a really high eccentricity, okay, like Halley's Comet, which comes around, orbits every 75 years, having a very elliptical orbit, it has an eccentricity of like 0.97. So anyways, our answers to number 11 is that planets orbit in ellipses. Okay, all right, number 10, or sorry, number 12. Why do orbiting bodies move faster at the perihelion than the aphelion? So if this is our ellipse, right, and the sun, okay, is going to be at one of the foci. And when you have a planet or a comet or an asteroid, something like that, when it is orbiting, right? So this right here, when it is at its closest approach, is called the perihelion. Okay. Well, when it's at this closest approach, that's when the force of gravity is the greatest, and therefore greater force, greater acceleration. Greater acceleration is going to be greater velocity, all other things being the same. So it's going to be fastest when it gets here, and it's going to be slowest when it's out here at the aphelion. Okay. The next question, okay, that was question number 12. What conservation law is responsible for planets sweeping out equal areas in equal time? You guys, this is Kepler's second law, okay, and it basically said if you have a planet, let's say, coming around here like this, okay, the area from here to here would equal, let's say, the area from here to here. So obviously, the distance, like the arc length that if we took over here, is going to be much greater than the arc length there, okay? So how could the areas be the same? And it has to do with, you guys, it has to do with the conservation of momentum. So the answer is conservation of momentum. So number 13. And sorry, that's conservation of angular momentum. Which would, and we obviously have used L for that variable. Okay, so number 14, the asteroid Icarus, though only a few hundred meters across, orbits the sun like other planets with a period of 410 Earth days. Determine the mean distance from the sun by using the mass and the orbital radius of the Earth. Okay, now, you guys, we don't need the mass. We need the radius. Okay, So I apologize for that. So we need the radius. And if we look up the radius between the Earth and the moon, so the Earth and the sun, that is 1.5 times 10 to the 11th. Okay, so we're going to use Kepler's third law, which the ratio of the periods of two objects orbiting the same thing, like the sun or the Earth, the ratio of the periods squared is equal to the ratio of the radii cubed. All right, so we know that in this case we're going to have Icarus and the Earth. We're going to have Icarus and the Earth. And what we want to know is what this Ri is. And so we can say that this is going to be equal to the cube root of the period squared times the radius of the Earth Sun cubed divided by the period of the Earth squared. Okay, so now remember, if we have the Earth and it's going around, we can kind of think of it as a radius with the sun, and that's just really the Earth-Sun distance, which is 1.5 times 10 to the 11th. Okay, so again, we'll plug these numbers in. Okay, the period of Icarus, as we already said, was 410 Earth days squared. The obviously the period of the Earth going around the sun is 365 days. Now, you guys, you might have noticed that we did not change that into seconds. We did not change that into seconds, which we would whenever you use the constant big G, the gravitational constant. You've got to have everything in meters and in seconds. But because we have days squared over days squared, they're just going to cancel each other out. All right. So now we're going to have 1.5 times 10 to the 11th, and that gets cubed. Okay. So if we plug this number in, 410 squared divided by 365 squared times 1.5 times 10 to the 11th cubed. And that is 4.25 times 10 to the 33rd. But we want to take the cube root of that, and we're going to get 1.62 times 10 to the 11th. So our answer here is 1.62 times 10 to the 11th, and that is the radius of the orbital period of Icarus around the sun, 1.62. So obviously that's farther away from the sun than the Earth, which is at 1.5. Okay, now the next question is, if the orbital period is 688 Earth days, and that's supposed to be Mars, okay? If the orbital period of Mars is 688 Earth days, between what two planets does Icarus orbit, right? So we're going to be somewhere between 410, 365, and for Mars, it would be 688. And so Icarus is going to be somewhere between Earth and Mars. And if you look up the mean radius of Mars, give me a second. Remember that in your textbook, this little flap at the front there on the back side, it gives you a bunch of information on the planets, and Mars has a distance from the sun that's 2.28 times 10 to the 11th. So Icarus is a lot closer to the Earth than it is to Mars. All right. So that gives us, brings us to question 16. If the semi-major axis of an orbiting planet is doubled, how does that change the period? How does that change the period? So remember, the semi-major axis and the radius essentially works. It's essentially working the same place. So if we have, and we're going to go up here to question number, what are we? 16. So this radius and the semi-major axis is going to essentially work in a similar manner, and therefore we're going to have t squared is proportional to a squared, sorry, a cubed. Okay, so if we double this, we're going to get the square root of 2 cubed. And the square root of 8, which is 2 cubed, is going to be 2.8. Okay, so the period would increase, the period would go up by a factor of 2.82. So 2.82 times greater. All right. Now, problem number 17, calculate the mass of the sun by using the orbital period and radius of the Earth around the sun. Now, this kind of goes back, and we did a question like this as an example. What is the mass of the Earth? And also in one of the questions of the day, what was the mass of the Milky Way? All right, so again, the logic goes like such. We're going to have the force of gravity, which is going to be equal to big G, the mass of the sun times the mass of the Earth divided by the radius squared. And since it's going in a circle, that's going to be mv squared over r. Velocity is equal to 2 pi r over t, which is the total circumference divided by time. Velocity squared is equal to 4 pi squared r squared over t squared. We're going to plug that into there. And when we factor all that out, right, this is going to cancel out with that. And now we can end up with the mass of the sun is equal to 4 pi r cubed. Now notice that one of these r's cancels out, but this r comes up here, which is a square, which becomes r cubed. We're going to have t squared down here, and then we're also going to have g. All right. So you guys, if I went too fast on that, then you guys can look in the book. There's a nice example on how to do that, or go back and look at my first lecture on gravity. And so we're going to say 4 pi. Now remember, this r, that's not the radius of the Earth, that's that orbital radius, which is 1.5 times 10 to the 11th, and that gets cubed. And now we're going to have 6.67 times 10 to the negative 11th. And now we want the period, but because we're using g, okay, we've got to have that in seconds. And that is a little over 31 million. And just let me walk you through that. So we have 365 days times 24 times 60 times 60, which is going to be 3.536000. Okay, so 31.536 times 10 to the 6th seconds to the 7th. Yeah, 31, or decimal point there. 31.5 million, and that's going to get squared. Okay, so and multiplying this out, And we're going to get a 2 times 10 to the 30th. 2 times 10 to the 30th. And that is the mass of the sun. Okay, so that would be in kilograms. All right, and that is question number 17. All right, so for the rest of, for the most part, the rest of our questions, we're dealing with a satellite that has a mass of 200 kilograms, and it is orbiting at an altitude of 3,600 kilometers above the Earth. What is the gravitational potential energy of that satellite with respect to infinity? All right, so here, this is going to be the Earth, and so now we're going to have this satellite that is orbiting here, and this altitude right there is going to equal to 3,600 kilometers, okay? But remember, our orbital radius is going to be the radius of the Earth plus 3,600 kilometers. So our total radius at that point is going to be 3,600 times 1,000. Okay, that puts it in meters, plus 6.37 times 10 to the 6, which is the radius of the Earth. And we're going to get 9.97 times 10 to the 6th meters. Okay, so that's the radius. That's the radius we're going to use. Now, again, we've gone through this, but the gravitational potential energy is going to be equal to negative G, in this case, the mass of the Earth, and that is going to be 1 over our final minus 1 over our initial. Okay, so essentially what we have, if we're talking about relative to infinity, this is going to be 1 over infinity, which is just going to go to 0. And now we just have whatever radius we were talking about. So this is essentially just going to turn into, this. So now we can calculate our gravitational potential energy, and that is going to be 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, divided by our radius here, which is at 3,600 kilometers, which is 9.97 times 10 to the 6th. And notice that's not squared. And we're going to get 4.0 times 10 to the 2, 4, 6, 7. I'm sorry. Looks like to the 7th joules. You guys, I just want to double check that. 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th divided by 9.97 times 10 to the 6th is equal to 4 times 10 to the 7th. Okay, that's going to be joules. But notice here we have this negative, okay? So this is the gravitational. That's the gravitational potential energy relative to infinity being 0, right? So that seems weird, but that's how we deal with that. And we'll see that if we're going from a lower orbit to a higher orbit, which would require positive energy, we'll see that works out. All right. So what is the tangential speed? What is the tangential speed of our satellite. Okay, so now remember what's making this go around, and this was question 18. Okay, and so we're going to have g, the mass of the Earth times the mass of the satellite divided by the radius squared is going to be equal to mv squared over r. Okay, so we want to know, this would be the orbital speed. So this is what we're looking for. So this m is going to cancel out. This r is going to cancel out. And then we're going to take the square root of that, and we're going to get v. Okay, so we can take the square root of 6.67 times 10 to the negative 11th, 5.98 times 10 to the 24th, okay, divided by 9.97 times 10 to the 6th, okay? And then we are going to take the square root of that. And all right, so we're going to get 6.3 times 10 to the third. Okay, 6.3 times 10 to the third meters per second. That right there is going to be equal to essentially just the square root of that. Okay, so I just want to check some numbers here. Okay, so moving on, what is the determine the orbital period of this satellite, and we could do this, you guys, we could do this in different ways, but we know that velocity is equal to 2 pi r divided by t, okay? And we know that the radius is 9.97 times 10 to the 6th, and we now know that the velocity is 6.3. I'll add the 0.25 times 10 to the third, and this will give us our period. Okay, so so 2 pi times 9.97 times 10 to the 6th divided by 6.32 times 10 to the third is going to be 9.9 times 10 to the third seconds. So if we divide that by 24, that's going to give us 410 hours. This seems wrong. Hold on a second. I'm going to go back and double check this because this seems wrong. Sorry about that. This is correct. I was trying to determine how many days that was, and so I want to divide this by 3,600 and divide that by 24, and we're at about 0.11 days, which makes more sense because we're going to have to get up to an altitude of 360,000 kilometers, right? I mean, before we have a geosynchronous orbit, which would have a period of 1 which would have a period of 1 day. So obviously we're at a much shorter or smaller altitude, so that it would have a period that would be much shorter. Okay, so on to some of our last questions here. What is the total energy? What is the total energy of the satellite? And remember that the energy of an object in a stable orbit is going to be equal to negative GMM over 2R. And you guys can go back and kind of look at that, the way that's developed, or you can look on page 376. But essentially, this is the kinetic energy plus the gravitational potential energy is equal to that. And the velocity in here is going to be equal to this. And then when we square it and subtract, then we're going to end up with this. So we're going to have big G, and this, well, we can put it in 6.67 times 10 to the negative 11th. Okay, so here is going to be the mass of the Earth, 5.98 times 10 to the 24th. Okay, the mass of the satellite is 200, and 2 times that radius, which was 9.97 times 10 to the 6th. Okay, and that is going to give us, an answer. Let's see, 6.67 times 10 to the negative 11th. Sorry, 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th times 200 divided by 2 divided by 9.97 times 10 to the 6th. And that's going to be, it's just our answer from right over here, right? So we're going to have negative 4 times 10 to the 9th joules, because we multiplied this by 200, okay, and we divided by 2, so we end up having the same number, except it goes up by a factor of 2 magnitudes, and this 2 and this 2 sort of cancel each other out. All right, so this is the total energy of that satellite at that altitude. Okay, so calculate the minimum energy needed to change the altitude from 3,600 to 7,200 kilometers. All right, so now we know the energy, you guys, we know the energy at 3,600. So what we're going to do is we're going to add 3,600. We're going to add 3,600 kilometers to this, going from 36 to 72. Now, you guys notice that we can't just double it, right? So we're doubling the altitude, but we're not doubling the radius. We are doubling the altitude, but that does not double the radius, because we still have the radius of the Earth. All right, so 9.97 times 10 to the 6th plus 3,600 kilometers, multiplied by 1,000, okay? And we're going to get this part right here is 1.357, okay, times 10 to the 7th, okay? So we're going to multiply that by 2. That gives us the denominator. I'm going to invert that and multiply it by 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th times 200. and that is going to be negative 2.93 times 10 to the 9th joules. Okay, now notice that they are both negative. So when we want to calculate that minimum amount of energy to take it from one altitude to another, we're basically talking about the change in energy, which is going to be energy final minus energy initial. So our final is 2.93 times 10 to the 9th, but that's negative. And now we're going to subtract a positive, or we're going to subtract a negative, which is going to make it positive. So we're going to say plus 4 times 10 to the 9th. And we're going to get a positive answer of 1.1 times 10 to the 9th joules. Okay, so you can see that that is an example. Even though our potential energies come out to be negative, negative and negative, when we want to talk about energy to go from one place to another, it's really just the change. It's the change there. So now remember, that's not just the change in potential energy. Okay, that's also adding in kinetic energy, because this equation right here is kinetic plus potential, which the formula is already combined for us. Okay, so now we have one, you guys, we have one final, we've got one final question here, and that is going to be, what is the escape velocity? And the escape velocity is going to be equal to the square root of 2 me over r. Okay, now we can, it doesn't really say in the question, is that the escape velocity from the Earth, or is that escape velocity from the 3,600 kilometer radius, or the 7,200? We're just going to do it for the Earth. We could add in either this 9.97 times 10 to the 6th for here, or we could do this for the 7,200, and we're going to get slightly different answers, but we'll do it for the Earth. Okay, so we're going to have 2 times 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th divided by 6.37 times 10 to the 6th. And then we're going to take the square root of that. So 6.67 times 10 to the negative 11th, multiply by 2, multiply by 5.98 times 10 to the 24th, divided by 6.37 times 10 to the 6th. And then we're going to take the square root of that, and we're going to get 1.1 times 10 to the 4th. So the escape velocity is 1.1 times 10 to the 4th meters per second, which is about 25,000 miles per hour. So the escape velocity, 25,000 miles per hour to escape the velocity of the Earth. Okay. All right, ladies and gentlemen, that's it. And good luck. And we will see you next time.